Okay. So now I want to be more explicit about what this category is that was introduced by Kuyava and Tharp. So that's the next section. The paraplectic Brauer category. So as already mentioned, the set of objects is just the natural numbers. And so now I want to talk about the morphism spaces in that category. So the morphism space between two natural numbers has a basis over C. So it's a C linear category. The basis of what is known as IJ Brauer diagrams. So here I don't say super or paraplectic because these are actually just the ordinary Brauer diagrams. It is their composition which will be new, which will be different. But a priori the spaces are the same as they would be in the classical case for OSP or orthogonal group or something. So the IJ Brauer diagrams, they are just a partitioning of I plus j dots into pairs. So a priori this only depends on I plus j, which is good for this type of morphism, of course. But to have them as diagrams, we put the j dots on the upper horizontal line and the I dots on a horizontal line below it. So we will diagrammatically represent this partitioning into pairs by just drawing a line between two dots which are in the same pair. So it's only the dots they connect which is relevant, not the way we draw things. So some examples of Brauer diagrams. So the 0R Brauer diagrams consist of just one line of dots, because then the second line I would be 0. So we just have some line of dots and some pairing them up, for instance like this. This is a 0,6 Brauer diagram. So of course here we find precisely the invariance that we saw in the result by the linear and Zhang. So the morphisms like this should correspond to homomorphisms from V to the power R to C. So here we can already see how that works. This corresponds precisely to the functions I wrote down. I just pair up arbitrary elements of the tensor power together using the bilinear form. So more generally, for instance, 2,4 Brauer diagrams. Some examples are given by this. So I just drew these to introduce some terminology. So we have some lines in the Brauer diagram. These lines, which both end on the upper line, are called cups. These ones are propagating lines. And these are caps. So based on what we already observed in this example, under the functor that we'll have from this category to the category of modules over the paraplectically superalgebra, we'll find that the cap corresponds to the bilinear form, which takes v to the power to the second power of v and maps it to complex numbers, so kind of diminishes the number of dots that we'll have. And that's the cup. And the cap will work in the opposite direction. So that's just the dualization. If I use the self-duality of V, it means that if I have a morphism in this direction, I should have one in the other direction. And that's precisely what this cap will be. And the crossing, so this diagram is kind of built up out of cups and caps and crossings, should be a morphism from V second tensor power to itself. And that's just the action of the symmetric group. In other words, I just exchange A and B, again up to possible minus sign. So that's just a rough interpretation of these diagrams in terms of morphisms for the modules. So the question is how to compose morphisms in this category. So morphisms are given by diagrams like that. Now I should explain how they should be composed. So since the morphism spaces have a basis by diagrams, it's enough to define how I should multiply two diagrams. So I'll first mention what happens classically. So for the ordinary Brauer algebra, there's also a way to compose these diagrams. So this is relevant in the invariant theory for OSP M to N. So then the composition of morphisms, the composition of diagrams, is just given by concatenation. So for example, if I want to compose these two diagrams, so that's well defined because this is a morphism from 2 to 4 and a morphism from 4 to 4, so I can compose them. So because I can compose them, the number of dots on this line coincides with the number of dots on that line, and I can place one diagram on top of the other. And then you just join them up. Okay, the diagram like this. And you recall that the only thing which is relevant in the Brauer diagram is the way in which the dots are connected. So I can just simplify this whole movement here by a straight line, same here, and I get demonstrate that. So one thing which isn't mentioned in this example is what happens if I get a loop in the diagram. So this just happens to be nice in the way that all the dots here are connected, all those there's nothing additional. But you could of course get loops, and they will be just removed from the diagram and replaced by multiplication with some constant. So then you don't necessarily get a diagram, but you get a diagram multiplied with a constant, which makes sense inside this space. So this space is a linear combination of diagrams, so in particular a number times a diagram makes sense. So if it's for OSP m to n, this constant will actually be m minus 2n. But so that's the classical case. That's not what we need. We need the composition of these diagrams interpreted as morphisms inside the perplectic Brauer category. And so it's very close, but a lot more intricate. So it's actually the same up to possible minus sign. So if you have two diagrams, it's very easy to compute their composition up to a potential minus sign. So that's the only thing which can happen. Unfortunately, to compute that sign is quite a lot of work. So it's very handy on one hand that you know what the multiplication is almost, but then it's quite annoying that the minus sign is rather hard to retrieve. So I'll just explain how one determines the minus sign. So the first thing that you should do is to give some decoration to the diagrams. First step, we decorate the diagrams. So I'll try to explain what that means by an example. So if we would start from this Brauer diagram, we'll add some decoration, which makes the diagram look like this. So I'll add a diamond to any cup, and I'll add an arrow to the right to any cap. And I've also drawn it in a way that no decoration is on the same horizontal line. And the order I chose for this decoration is as follows. I only look at the leftmost dots of cups and caps. I order them from left to right, and then down from right to left. So I go around the diagram like this, look at the leftmost dots on each cup and cap, and choose this order, and then the latitude of these decorations should represent that order. So this is 1, 2, 3, 4, 5. Keep ascending. Okay. So that's how to decorate a diagram. Then we want to actually multiply two diagrams. We concatenate the decorated diagrams And of course, we're not allowed to interchange the relative latitudes of the decorations that we have. So for an example, I'll choose some different diagrams than the one which I had up there. So the reason for that is, if I will now multiply two diagrams, this part, so if this is the left diagram or the upper diagram, this part won't play any role. And neither will the bottom row of the second diagram. So that would just add dead weight to the computation, which I'd rather avoid. So that's why I take here a diagram with only caps and here only cups. That would make a difference. So if I can compose these two things because I have 6 dots here and 6 dots there. So I do what I tried to explain there. I add the decoration in the correct way. So I've just put one diagram on top of the other with the decorations in the order that I explained here. So again, we just join up the two diagrams. And now there's a number of rules that we're allowed to apply. So we want to bring this into the standard form. By which I mean the following. So we have again some decorated diagram, but it's not in this standard form. I mean the order is not preserved, and I have multiple decorations on one line, so I somehow need to get rid of all of that. So what I'm allowed to do is, if I have an arrow pointing away from a diagram on the same line, I have to multiply the whole diagram with -1 and get rid of those two symbols. If the arrow points towards the diamond, I can just remove them without a sign. And also we have to multiply with -1 if we exchange latitudes. So if we do that here, the first thing we can do is get rid of these two, because they have adjacent latitudes, but I get a minus sign because the arrow points in the other way. So this is minus this diagram. In the end, all the arrows should be below all the diamonds. So I get minus, oh sorry, I've also flipped this thing around, so I should keep track of which way the arrow points. So I get this, but then still the arrow is in the wrong direction, and that's the fourth rule, which I forgot to mention. If in the end we have an arrow pointing in the wrong direction, we have a minus sign as well. So we get minus this diagram, and then it's in the appropriate form. So then we can get rid of the decoration again, and we find a minus sign. So that's a whole lot of work to compute the composition of those two diagrams in this category. So we would know that it's plus or minus this diagram on site. But to determine the minus sign, it can be tricky. So yeah, this whole construction is due to Kujawa and TARP. I should stress again. So I'll give some more examples which are rather easy but quite central. So for instance, a crossing after a cup. So the decorations are quite easy. So this composition is just a cup again. So that's good because this bilinear form is supposed to be symmetric. And given the interpretation here of the cup, which is just a bilinear form, and a crossing which is just flipping, this is nothing else but saying that the bilinear form is symmetric. So another one we can compute is the cap and the crossing. So then the decoration is an arrow. I have the crossing, and just like we've seen before, this is actually minus. So this composition is minus the cap. So what that means, and that's something that you can compute by hand, because the odd form, even though it is symmetric, but because it is odd, the dualization is a morphism which has image in the skew symmetric power and not in the symmetric power. So if I take the morphism from C to V tensor itself, and I apply the generator of the symmetric group, I get minus that one. So that means precisely I'm in the skew power. Okay. So now that we've computed these two, we can also look at what a loop does. So that's something which I haven't mentioned yet, but now you can just compute it. We've just seen that a cup is the same as crossing times a cup. Hopefully everything is associative, which is a non-trivial thing to check. But if it would be associative, which it is, I can combine these two, and then if I perform that composition, I should get a minus sign. So this diagram is equal to minus itself, so it should be 0. Which is not surprising because the superdimension of our space is 0. And like we've seen for OSP, usually one gets the superdimension there. Okay. An important property of that category is that it is monoidal in some sense. So that category is a monoidal, and to be precise, it's a monoidal supercategory. So I won't go into detail what the subtlety is there. So it's of course something to do with some minus sign when we exchange certain things, so that it's actually not really a monoidal category in the strict sense. But I think we can skip the details of that. So the tensor on objects is given by the tensor of two natural numbers is just their sum. And on morphisms, well, if it would be the ordinary Brauer category, we would just place one diagram next to the other and get a new diagram. It's again the same up to a potential minus sign. But we don't have to do any additional work, because you could define it, for instance, in this way. So if you have two morphisms, or which are diagrams, so let's maybe better to make it precise. So let's take an IJ Brauer diagram and a KL Brauer diagram. Then you could define this as follows. So I hope I didn't make a mistake there, but it's supposed to be the number corresponding to the amount of dots on top of that diagram and the number of dots on bottom of this diagram. And by one, that I mean the identity morphism of that object, which is just a couple of straight lines. So of course, then I still need to define what the tensor is with this one, but this is just really actually putting the number of straight lines to the right of this diagram and to the left of that diagram, and then use composition of diagrams like we've explained, so that the same rules appear. So you could think about it as just specifying, put this diagram in a box here and the other one there. So their tensor power is given by this, but to merge them together you again need to take care of the minus signs. So you could also just say we decorate this diagram and that diagram and then just shift everything into position. So then it's possible to specify what this functor is, I've already mentioned. But I think it should be more or less clear now. So the functor from the paraplectic Brauer category to the category of tensor powers of the natural module over the paraplectic Lie superalgebra. It is a tensor functor. Of course. That means that we don't need to give a lot of information to define it. For instance, it's sufficient now to say that 1 is mapped to the natural module, that as already explained there, the cup is mapped to this morphism, that the cap is mapped to the dualization, that the crossing is mapped to the morphism specified there, and then everything else is generated by tensor relations. Once I have these three diagrams, well, also I suppose the identity morphism, then I can construct any diagram by composing and tensoring. And if I specify this and it's a tensor functor, then this means automatically that I must be mapped to the ith tensor power of that one. So it is a unique tensor functor with these properties. I hope it's clear. I didn't specify which morphisms because they're the ones that I tried to describe earlier on. One easy consequence of this monoidal category structure is something which I will need later on, so I'll just state it explicitly. It means that the tensor power of AI and AJ, so these were the paraplectic Brauer algebras, which are the endomorphism algebras of the objects I and J in this category, is a subalgebra of AI plus J. Precisely by this idea here. I put the tensor of the I diagrams and JJ diagrams together like this to get an algebra morphism like this. So we'll also choose a corresponding embedding of any AT in AR for T smaller than R, where basically any element in here, so any TT Brauer diagram, is mapped to F times and then R minus T straight arrows. So I just want to fix that, that I don't have to specify it anytime. So there are many different ways in which we could consider this as a subalgebra. I just want to fix that one. Okay, so that's the end of the first chapter. I don't know if there are any remarks, questions now. Yeah.
Do you have any physical realization of P?
It depends what you mean by physical, but it does appear as an algebra of symmetries of what is known as the odd Laplace operator. So if you would take a superspace, for instance, a flat supermanifold of dimension nn, then something which appears in physics is the odd Laplace operator, which, for instance, you could write like this. Where xi are the n bosonic variables and theta I are the n fermionic variables.
So those D are Dirac or just ordinary D?
Yeah, partial derivative. Partial
Just
derivative.
partial.
Yeah.
Okay.
So, I mean, I choose these such that the algebra of polynomials is just the algebra generated by xi and theta I and have the corresponding partial derivatives. So, just like for the usual Laplace operator,
But this is not equal.
no, I guess not. Yeah, no.
So how could you study the spectrum?
I don't know what is precisely studied.
It's not written is in general hopeless.
Yes, but yeah, it has appeared in certain physics papers, and naturally, the paraplectic supraalgebra has a realization which commutes with that. So that's one physical realization that I know of. I don't know much details about why it appears and what the use is of the paraplectic supraalgebra. It does appear.
Because theta is a formula. So in general,
Yes.
d theta and I is really not the differential operator. It's some kind
Yeah.
of algebra key in
Yes.
one form, two forms.
Yeah. Yeah.
So I regard this really not the
Mm-hmm.
ordinary kind of differential operation.
Yeah. No. Yeah. It's yeah.
I will regard it really just first order in ordinary space, in Morgan space,
Yeah.
with some kind of jet data.
Mm-hmm. Yeah. Yeah. You could see it, as you say, on just ordinary space and then differentials added to it, and yeah.
I think the physicists were the one who discovered this algebra first.
Yeah.
That's the funny thing. The physicists discovered
So I think both P and Q
and Q.
were known before the classification.
Yeah. So it's, I think it's classification of classical simple superalgebra. It's actually due to they are showing up now.
Okay.
A few months before Katz,
Okay.
75. So
Yeah.
but Katz did found those HS and
Mhm.
W.
Yeah.
So this Katatanka.
Yeah.
Those they didn't know. Otherwise they would put it down.
Yeah. Ah. Okay.
That was his
Yes.
understanding. Because Katz knew it because he worked on this characteristic P.
Mhm.
And those are simple. These
Yeah.
are other characteristic P. So he knows these things.
Okay. Yeah. You're right.
I think that was just true.
That's-
Those classical and those the physicists they did that. They knew about this.
Mhm. Yeah. Yeah.
And then about this exception, the funny thing is that they were discovered. This one, I mean, they proved the existence, but they were suggested earlier, 2 years earlier by Kaplansky, when he was looking at the Z2 grading superalgebra. So it's really very funny history.
Yeah. No. So I think there's about 20 minutes left or so. So I think I can say a little bit, give an introduction to the second chapter about the representation theory of this algebra, AR. So the approach that I took in the first preprint of the theory I mentioned is a bit of a trick by actually first studying a different algebra, which I called CR. So I actually have, while preparing for this lecture, found new respect for that approach, because I wanted to omit it and say I'll just do things directly, and it seems that the direct way is somehow more complicated. So I will introduce it in the way that I did it in the preprint. But so there are many available techniques which could have been used to come up with the results that I will present, which work just fine and which are more general. So I think this goes back a bit to the introduction of cellular algebras by John Graham and Gustav Wehr. So they introduced cellular algebras, which is kind of based on the ideas appearing in the study of the symmetric group algebra and the Hecke algebra. And so it's been studied by many people. For instance, quite closely after the introduction, Stefan Koenig and Chang Shi gave some alternative ways to deal with the same types of algebras. However, this algebra isn't cellular, but still the only thing which goes wrong is the involution which is required for that definition. But shortly after this work, in some work by J. Du and Hebing Rui, they proved that the same techniques all survive when you omit the involution in what they call standardly based algebras. So all of this was done in the 90s, the development of these types of algebras, and one could really apply this without any problem to this algebra. I'll follow a more recent, also a more specific idea, which was in a recent preprint that I had in collaboration with Ruben Zhang. Which is to start with a different algebra, which can also be defined using this paraplectic Brauer category. So the definition is as follows. So this set J of R is a set which will be familiar to anyone familiar with the Brauer algebra. So I take R, but also R minus 2, R minus 4 until I start to run into negative numbers. And I can equip this with an algebra structure by using the category structure. So the composition of two morphisms is 0 if the objects don't match, and if the objects match, it's just a composition of morphisms in the category. So in particular, it contains AR as a subalgebra, which is just this subalgebra. So, why is this an interesting trick to do? Well, just the following observation: any Brauer diagram is of the following form. So let's say any Brauer diagram D is of the form D1, D2, D3, to give some very uninspired names for the diagrams which appear, where D1 is of this form, D2 is of this form, and D3, for instance, something like that. So a very elementary observation: any diagram we can see as a product of something which doesn't have caps and no crossing propagating lines. Something which has no caps and no cups. And something which has no cups and no crossing propagating lines. So this statement is something for which the diagram calculus is very nice, because you don't need to worry about signs. But any diagram I can kind of tear apart in this way. I just put all the cups, then all the crossings and all the caps. The simple advantage of this algebra is that all these three diagrams are still inside the algebra. I can do this for any diagram in the perspective Brauer algebra, but then the sub-diagrams won't be elements of the algebra. So this is the only advantage that there exists. So this kind of gives a triangular decomposition of this algebra CR. Triangular decomposition in the sense that it's similar to the way that for a reductive Lie algebra you can write this as a consequence of the PBW theorem. So that's how you can look at these things, as somehow positive roots, a Cartan, and negative roots. So in this analogy, the Cartan, or its universe in developing algebra, its role is taken over by all these diagrams, so which is the subalgebra given by symmetric groups algebras. And then you can really apply the same ideas as you would do in category O, for instance. We start from a module over this algebra. We let the positive roots act by 0, and we just induce up like this. And we can construct standard modules that way. So the simple modules of that subalgebra, let's call it capital H or something. So because we're working over the complex numbers, this algebra is actually semi-simple. So in positive characteristic, it's more complicated, but still the same idea somehow works and gives everything. But here it's rather straightforward. So H is semi-simple, and the simple modules are given by the spect modules. No. No, because this is not an element in AR. It's that's just what it is. So the simple modules are given by the spect modules, which I write like this: W0. So I write W0 because then we'll have the cell modules for AR later on, which will be W. So for any symmetric group on I symbols, its simple modules, its spec modules, are labeled by the partitions of that I. So here I just take all the I's together and construct all the simple modules of that H. So then it's really just the same as you would, for instance, do in the category O. The simple modules for CR are labeled by the same set. Because for any such module here, I can induce some standard module there. I have a nice triangular decomposition. I get a unique maximal submodule, a quotient, etc. So, of course, one has to work a little bit, but it is really not very hard using that triangular decomposition to get the following theorem. I'll introduce notation LR for this set of partitions. So almost by construction we get a quasi-hereditary structure, which basically means it behaves like, I don't know if I need to introduce quasi-hereditary algebras. Yeah. I'll mention, so we have some standard modules. I'll just mention what quasi-hereditary algebras are. So some finite dimensional associative algebra is quasi-hereditary for some partial order on, let's say, lambda b, where this is a labeling set of its simple modules. So there are many equivalent definitions, I think. I'll just give the one which is most intuitive, which is a representation theoretic description. So if you have some partial order on lambda b, it's a labeling set of simple modules. If there exists some particular modules, often written as delta of lambda. So such a module must exist for any simple module. So for any simple module, there's an accompanying standard module with the following properties. So the simple module should appear as a subquotient precisely once in the corresponding standard module. And all other simple modules which appear in the standard module must be bounded by lambda in the partial order. So this simple appears 1 and everything else is lower in the partial order. Then you must also have that projective modules. So any simple module has its corresponding projective cover, and those must have a filtration with sections or the factors given by standard modules. And moreover, the number of times such a standard module appears in this filtration should satisfy similar conditions. So the corresponding standard should appear once, and otherwise everything which appears should be higher now. So they're basically algebras which have a certain class of modules which lie in between projectives and simples. And the filtration of the standards by simples is triangular in one direction, and then the filtration of projectives using standards lies in the other direction. And of course the typical example is category O for a simple Lie algebra. So I think time is run out anyway now.